Alright, welcome to another AQA A-Level Chemistry video. Today I'm going to be doing a video on experimental methods for rates. So this video is talking about more of the practical skills related to rates of reaction. And that's the, if you think about it really, rate of reactions are mainly needed to be used for the practicals. You need to be able to collect the data from practical and use that data to plot a graph, and then be able to then work out the rate of the reaction. That's why it's important, right? But the reason I say this, because obviously I don't do a lot of practicals on this channel for obvious reasons. I haven't got the resources. But I make this video because everyone knows the content, or everyone knows about how the steps are associated with the practical, right? But they don't really make emphasis of the skills that would have been associated with answering that question, right? You know, everyone knows about how this step is the net least, and this step. They don't emphasize on how they collect that data, and they don't think about the obvious, the small things like how often were you collecting data, and were you collecting in regular time intervals. Okay, there's the simple way of working out the rate of reaction, but you have to, scaling, doing a graph and doing a tangent at t equals 0, and then working out that way. But there's also other ways of working out the rate of a reaction. And it's just about being able to say how you did it, how you worked out each step. And that's important in how they'll mark important in how they'll mark your answer. They'll say, because remember, these are going to be 6-mark questions, right? And they do the band 1, band 2, band 3. And if you want to be in that band 1, band 3 will be the highest band, I think. Anyway, if you want to be in that highest band, you need to mention every single bit of detail. So, and one of the things is how you go about collecting your information to work out your initial rate of reaction. Anyway, enough waffling now, I'll get straight into the video. So the initial rates method can be used to find. Also, at the end of this video, I'll be doing the some exam style questions if you need it. So the initial rates method can be used to find the rate equation for a reaction. So initial rates method. The initial rate is the rate of the reaction at the beginning of the reaction. And if you measure the initial rate over a variety of concentrations of a reactant, you can work out how the rate depends on the concentration of that reactant. So to find the initial rate, we construct a tangent to the graph at t, or time equals 0. And be sure to do this at the beginning of the rate section. I'll leave a link in the video to that first video when I showed you how to do a tangent. Should have been the very first video of this section, of this unit, right? But what I just want to bring this point here, right? It says if you measure the initial rate over a variety of concentrations of a reactant, you can work out how the rate depends on the concentration of that reactant. So if we're doing multiple reactions, right? So this is going to be we're going to be comparing multiple graphs, and each graph represents a reaction, but the concentration of that reactant is different, right? So if I did, should I do a, yes, little one, probably at the very end. So say this is one graph. I'm just doing this freehand. I'm not trying to make this all ton of need to know that. I'm just trying to show you what I mean here, right? So let's say that this is the, let's say MgCl2 let's just say it is concentration of MgCl2 being produced. Yeah, let's go for that. Concentration of MgCl2 produced with 20 grams of magnesium, and then concentration, and have time here, and we have the same thing here, concentration of MgCl2 produced with 10 grams of magnesium. and let's say 10, both the same number of CO2. Right? So this is the same type of reaction, but we've just changed the concentration. Actually, this is mass. I'll use. Okay, you know what? Doesn't matter. Doesn't matter. I can use mass instead. I'll use mass instead of concentration. In this example, we're using the concept here will be the same anyway, because we're doing how changing them. If we're changing the mass or the concentration, concentration is about the mass in a solution anyway. But yeah, I'll use this example here, right? So let's say that this is the same reaction. So let's just say that we're going to be using differences in mass. So the same type of reaction, but the mass of our reactants are different. I'm not using concentration in this example. The mass of our reactants are different. And this is what we'll be doing. We'll be doing a range of, in theory, we'll be doing a range of different experiments where we have the exact same types of reaction, but we have numerous different types of masses or concentrations, and we'll be determining how that affects the rate of the reaction. So in your mind, you'd assume that this reaction, let's say that it go like that, and then this same reaction. Now, let's see, I'll put it back down here because it technically will be half, right? That's 30. That'll be 20. Okay, so it'll be a bit more than that. Right? So the point is here that you can clearly see that the higher the concentration of magnesium here, the faster the initial rate of the reaction. The initial rate of the reaction, as we said before, we do a tangent at t equals 0, which is, this is 0 seconds here, or 0 minutes, anyway, t equals 0, right? Let's actually get a ruler for this part then. Where's we got a ruler here? Yeah, we got a ruler here. Why isn't it going up? Here we go. There you go. Right, and then you do a little triangle doing from some point. Let's just say right. And if we did the same thing here, the point being, I know I've kind of dragged this out a little bit, but the point being here, what I'm trying to show you is that you can clearly see here there's a difference in our rate of reaction, our initial rate of reaction, where the reaction with a higher mass of magnesium has a faster initial rate of reaction compared to the other reaction which has a low concentration of reactant. Now, if you understand there's a video that I did on Maxwell-Boltzmann distribution where I talked about differences in mass and concentration. That'll explain why that one is. That's a terrible graph there. There you go. You can clearly see that this graph here is of, well, they're both terrible graphs, first of all, to make that clear. But this is what you're doing now. As you've clearly seen from the way I've done this, and you probably skipped on from this video right here, bro. This is a very, very long method of doing it. And the way you do it in your exams, or the way I've done it in the previous video where I showed you, and the way I'll be showing you in answering some of these questions, there's much faster ways of working out the initial rates of reaction and using it to work out the order of the reaction, than doing every single graph and then doing a tangent of every single point, because that's just long and unnecessary, right? But I'll be going into that. So I'll go into that, but first of all, I want to talk about one type of reaction, that's a good way of showing a good experimental method for working out the rate of reaction, and that's the iodine clock reaction, and it has a sudden color change. The reaction happens between hydrogen peroxide and iodide ions according to this equation, H2O2 plus 2I minus plus 2H plus goes to form 2H2O plus I2. And by varying the concentration of hydrogen peroxide or iodide, you can get different reaction times. So this is just an example of one type of reaction where we can just alter the concentrations of reagents that would be used, that would affect the rate of the reaction, and by just changing those concentrations we can therefore change our rate of reaction. So how does it work, right? So what you do is that you add sodium thiosulfate in starch to the solution. Now the sodium thiosulfate one is some people use different reagents, and different videos will use different reagents, but I believe for your exam, sodium thiosulfate is the one that you need to use. But if I'm wrong, look to your booklet, look at AQA. But this is from AQA Seneca, so hopefully this should be correct. But always go and check your curriculum just to make sure that it is sodium thiosulfate. But that's the only thing that's different here. But you add sodium thiosulfate and starch. Starch is definitely one that you need. I'll explain why. So you add sodium thiosulfate and starch to the solution. Now initially, the thiosulfate will react with any iodine formed and remove it from the solution. So any iodine that's formed when the hydrogen peroxide reacts with the iodide ions, it then react with the thiosulfates, and the thiosulfate would remove the iodine from the solution. But once the thiosulfate has been used up, any iodine that's been left will turn the solution blue black, because it'll be reacting with starch. Remember, iodine turns a starch solution blue black. So really here we're just determining by, if we alter the concentration of sodium thiosulfate here, or alter the concentration of hydrogen peroxide or iodide ions, really we change the rate of reaction, and then we can use that information to work out the order work out the order of each reagent, and being able to use that to tell us which reactants are in the rate determining step. And once we know what the rate determining step is, we can make a rate equation. You see that I know it doesn't say that here, but that's really what you're trying to do. You're trying to use this information here to you want to do multiple different reactions to help you confirm your understanding of how a particular reactant would affect the rate of the reaction, and then be able to use that to determine we believe that this effect has an order of 1 or 0 order, and then be able to use that to say, okay, now we have all this information, we know what the rate determining step is for this reaction, and then we know we can make a rate equation. Now I'm going to watch a small video of what this reaction actually looks like. It's a very interesting looking reaction. It kind of looks a bit like well, it's so instant, and yeah, I'll come back onto this after you watch the video. So
Okay, so I've decided to do a chemical reaction that, in my opinion, kind of looks like magic. The first thing that I need is a bit of cornstarch, and I'll mix this with some boiling water. A small amount of the cornstarch didn't dissolve, and to clear it up a bit, I'll just pour it through some coffee filters. It took a little while to finish, but when it was eventually done, I added some hydrogen peroxide. I'll mark this one as part B, and the next thing that I have to do is make the part A. To do this, I'll need some pills, and I picked up some vitamin C. I only need 2 of them, and all I have to do is crush them and mix them with water. What I'm doing here is pulling out the vitamin C from the pill and leaving behind a bunch of filler. Like before, I'll dump this into some coffee filters to clean it up a bit. Now that it's done, I'll add an entire bottle of iodine disinfectant. The color of it immediately disappears, and this is because the vitamin C is reacting with the iodine. On top of this, I'll add a bunch of water, and that's it for part A. Now, all I need to do is mix together these 2 solutions. At first, it doesn't seem like anything is happening, and it basically does nothing for over a minute. It takes such a long time that I often think I messed something up, but then it suddenly changes. This is called the iodine clock reaction, and I think it's pretty cool.
Now, just to say, like, you may have thought that was like an edit to make it look like really quick, but that's actually how it quickly happens in real life in the practical. It changes. It changes suddenly. During the reaction, and it's quite interesting to look at. But one key thing to look at here is that you now have seen how fast that reaction happened, and you're meant to be using a stop clock. So you need to be very vigilant during this part of the reaction. I've also left a link to the Primrose Kitten video, which will explain the entirety of the practical and what you need to do. And because I'm not going to go through that, I don't want to go through practical steps. I'm just here to show you, to explain content here on this channel. But one thing that is very clear to mention is that in the exam they want to make it very clear to you how are you going to address the fact that it's a sudden color change, because really when the color changes happen, that's the end of the reaction. So you need somebody to stop the stop clock when you see the color change. Now that means that you're gonna have someone with a quick sorry, I keep on stumbling here. Someone with a quick reaction time, but at the same time, quick reaction time isn't actually accurate, i.e. in terms of the fact that it's considered to be, well, human error, really. Now, for the sake of this practical, it's perfectly fine to have someone just doing it, but just having a think about how can I improve that to make sure that we reduce that factor of human error. And but we can just think about saying things like having the same person hold the stop clock, so that, because different people have different reaction times, so we get more conclusive evidence saying that this is the reaction time for this, this is the time for this reaction to happen. The reaction took this many seconds, this many minutes to happen, and it's conclusive because the same person did that reaction. But also, if you wanted to be a bit more over the top, one thing that you could do is you could attach a colorimeter to a computer that has a stop clock on it, and so when the colorimeter detects a decrease in the light intensity of your solution below a certain value, it instantly triggers a sensor. It instantly gets triggered to stop the stop clock. Now, that's a very high tech thing of saying it, but that's one thing that you could think about. Maybe you ask your teacher maybe if that could work, but it's just about addressing the fact that you're using your initiative to think about how to reduce errors in this experiment so we can get a very accurate value for our timing of the end of this reaction, so we get a very accurate, we can then work out a very accurate rate of reaction. Hopefully that makes sense. So That's what I mean there. If I didn't make sense, or if that didn't make any sense to you, leave a comment in this video on it, and I will try to explain it in a way that makes more sense to you. All right, so the next type of monitoring, or next type of way of determining the rate equation, is continuous monitoring. Continuous monitoring is actually something that you've probably already done it for most of your reactions. Continuous monitoring is just another method for determining rate equations, and Primrose Kitten actually did that in her video. It's just about continuous monitoring is just the name given to taking measurements of rates at specific intervals. So you tend to measure the change in the quantity of a substance, and these include loss of mass, volume of gas evolved, change in color intensity, or the pH change. So all this is just you saying that every 1 minute, every 2 minutes, or every 3 or 4, or even every 5 minutes, but not in that's probably a bit too long, but every minute or so you're checking, you basically you're recording data every minute. That's what you do in most of your experiments. You probably that is just continuous monitoring, where every interval, every specific interval. So if you say every 30 seconds, we're going to check if there's been a change in mass, or if there's any change in the volume of gas evolved, change in the color intensity, or any change in the pH. We're just checking that in regular intervals, or it doesn't have to be time. It can be, the interval could be in a volume. So if we're doing, for example, if you're doing a titration reaction, you can say once you get close to your titer volume, you can say every 2 milliliters we check the pH. That's an interval, right? So it's just something that that's just what it's called continuous monitoring. It's kind of like, okay, the one that came to my head right now, that I remember now, is to do with the calorimeter, right? You check the temperature every 30 seconds, every minute. That's just continuous monitoring, just continuous monitoring in intervals. The next one is colorimetry. Colorimetry can be best explained by looking at the redox titration. So colorimetry is another way of working out the rate of reactions. Now you learn a bit more about this when you study inorganic chemistry year 2. Inorganic chemistry year 2 gives a better explanation into how colorimetry is used, but I'll just talk about this here briefly. Is that redox titration? So titration is an experimental technique for finding the concentration of solutions, and it uses balanced equations to calculate the concentration of an unknown solution from a volume of known solution, so measured by a burette. The experimental technique often involves an indicator to measure the end point of a reaction, and a small volume of a solution is dropped from the burette into the reaction flask, and this is repeated until the indicator shows no further reaction happening. So if you should have done a titration. So titrations, you should know about how you have a small amount of your unknown small amount of your unknown concentration in your flask, and a very large volume of of your known concentration of solution in your burette, and you slowly drip that down into your flask, and then you'd work out the tighter volume. You continuously swirl the flask to make sure that it gets mixed, and from there you can then work out once there's an obvious color change because you have an indicator in there, you can then work out the tighter volume, and you can also use that information to help you work out the rate of reaction. How long did it take, or what volume of it did it take before the tighter volume was reached, and things like this. So this is just another way of working out rate of reaction. So colorimetry is all that. In terms of that's a titration, but how to actually understand a colorimeter, because colorimeters, remember, they're just measuring the light intensity, so they'll be better used for determining when the reaction has ended. So you don't need to. You'll learn a bit more about that when I do inorganic chemistry. But what I will say about colorimetry, it involves a good understanding of interpolation. Interpolation is just, remember, this is, if we're talking about graphs, Extrapolation is when, if you know a graph's like this, you can then assume that it's going to continue with that same trend. So if it's an exponential, you can assume that it's going to continue that same trend. That's extrapolating. Well, actually, technically, extrapolating would be going beyond your graph actually. But that's not what I'm going to talk about. We're talking about interpolating. Interpolating is when you read from within your graph. So say we have the graph line y equals x, right? We're saying if y is equal to a certain value, read to our graph. So that's a terrible line. You obviously use a ruler, don't be like me. But then you go down and say, that's all right. If y is equal to that, what will x be? And you're, by interpolating a graph, you're going from that value or your y value, or it could be x value. It could be going up from your x value to the graph, to the line on the graph, and then using that to find that value on the y. Either way, y or x, but that's interpolation. And you need to have, that's what you'd use for colorimetry, and that helps you out with working out when the reaction ended, so and so. You don't need to know too much about that until you go on to about colorimetry until you do inorganic chemistry year two. Sorry about that. So yeah, I know this video's been a bit of a mess. I've probably gone on and dragged this on a little bit too much, but that part of the video is done now. I'm now just gonna go and do a video on. I'm just gonna do. It's very late, guys. I'm sorry. I'm now just gonna do a small segment where I talk about answering some exam style questions. So I've got some exam style questions here worth 20 marks overall. 20 marks. I want you to try and answer these questions. I'm gonna pause the videos at the different times to help you go through every single question. All right, I'm gonna set a timer of 20 minutes. Actually, let's set one. Right, so I'm going to try. I assume you've paused the video and tried to answer those questions. So now I'm going to just start answering the question now. The following data were obtained in a series of experimental rate of the reaction between compounds A and B at constant temperature. Show the data in the table can be used to deduce the reaction is first order with respect to A. Show that it's first order. Well, as this doubles, as A doubles, as concentration of A doubles, the rate of reaction doubles, and this is stayed constant. So from experiment 1 to 2, as initial concentration of A doubles and concentration of B is constant, the initial rate of reaction doubles. And then mathematically, you can just say log base. This is increasing by a factor of 2. This is increasing by a factor of 2. Log base 2 of 2 is equal to 1. That's first order. Deduce the order with respect to B. So B doubles here, but this also doubles. But we know that this reaction is first order in terms of A. So when this doubles, this should double as well. So the initial rate of reaction should double. So 0.9 times 10 to the power minus 5 times by 2 is 1.8 times 10 to the power minus 5. And then work out how the jump between this from 1.8 times 10 to the power minus 5 to 7.2 times 10 to the power minus 5. So 7.2 times 10 to the power of minus 5 over 1.8 times 10 to the power of minus 5. Realistically, in your calculator, you just put 7.2 over 1.8 because the times 10 to the power of minus 5 will just cancel out. And that is 4. And b is doubling, so log base 2 of 4. Because remember, the order is just the power. And to work out the power, we can just do logarithms. Right? That's 2. That's how I would do it. Because really we're doing this 2 represents how much the concentration is doubling. That's 2. And we know that it's increasing by a factor of 4. So we're trying to work out what x is here. And we don't need to do that by using logs. And this x represents the order, so that's and x is equal to 2. So and that's very obvious here anyway, but that's what we're trying to mathematically show here. So therefore order of b is equal to 2. And I'll just put a rectangle around it. I just circle that one. The following data were obtained in a series of experiments on the rate of the reaction between compounds C and D at constant temperature. The rate equation for the reaction is rate R is equal to C squared D. Use data from experiment 4 to calculate value for the rate constant K at the temperature, state units of K. I think there's a little mistake with this here. This is meant to be C and this is meant to be D. Don't worry about that. If we're just working out K is just equal to R over C squared D. And that's just rearranging the equation now, so that's just all that is. 9.30 times 10 to the power of minus 5 all over 0.75 squared by 1.5, I think it is. Type that into a calculator. 9.3 times 10 to the power of minus 5. I'm sorry guys that I'm not as active as I can be. It's like quite late at night right now, and so I don't want to make too much noise. I'm just trying to do this. These videos are long because I'm trying to make sure that I explain every single part of it. It's not for me to try and bore you to death. I'm just trying to make sure you have everything that you need to answer these questions. And if you want me to go faster, leave a link in the video, and I can try to make these videos faster. But I'm just trying to make sure that I explain every single point for you guys. Anyway, units of K, it would just be moles to the power of minus 2, dm to the power of 6. And if you can't see that, it's because realistically, got this here, moles per dm cubed per second over moles per dm cubed squared by moles per dm cubed. Sorry, I kind of got off the screen. But either way, that moles per dm cubed and that moles per dm cubed here is cancelled out. And so we have s to the power of minus 1 over moles per dm cubed squared. So that's s to the power of minus 1 over moles to the power of minus 2 dm to the power of 6. Moles, my bad. Moles squared dm to the power of minus 6. But then it'll get flipped around because that's the same as this is the same as writing this. That's what that was there. Calculate the value for the initial rate of the rate in experiment 5. How much time have I got left? 12 minutes, 50 seconds. All right. R is equal to, we already know that what K is. 1.10 times 10 to the power of minus 4 by 0.2 squared by 0.1 0.2 squared by 0.1. I got 4.41. Let me just, does this count correct? 4.41 times 10 to the power of minus 7. Yeah, that sounds right. Anyway, if that sounds roughly correct. The following table shows the results of 3 experiments carried out at the same temperature to investigate the rate of the reaction between compounds P and Q. Use data in the table to deduce the order with respect to P and order with respect to Q. So P is halving, and the rate of reaction is, I think that's a quarter. Looks like a quarter. Now, knowing this, they do like to make it close enough. You just have to just check it, but it's a quarter. So log base 0.5 of 0.25 is equal to 2. So order of P is 2. This has doubled whilst that stayed constant. So this is stayed constant during that, and this is stayed constant during that, and this is just doubled. So 1, because you just got log base 2 of 2, which is equal to 1. Interaction between R and S, the order of the reaction with respect to R is 1, the order of the reaction with respect to S is 2, and the rate constant at temperature T1 has a value of 4.2 times 10 to the power minus 4, moles to the power minus 2, dm to the power of 6, s to the power minus 1. Write the rate equation for this reaction. Well, first of all, I could just do that. R is equal to K R S squared. Because it's already given us all the information there. And then calculate a value for the initial rate of the reaction when the initial concentration of R is 0.16 and that of S is 0.84. So R is equal to 4.2 times 10 to the power of minus 4. R is 0.16 and S is 0.84. 4.74 times 10 to the power of minus 5. In the second experiment, in a second experiment performed at a different temperature T2, the initial rate of the reaction is 8.1 times 10 to the power minus 5 moles per dm cubed per second, when the initial concentration of R is 0.76 moles per dm cubed and that of S is 0.98 moles per dm cubed. Calculate the value of the rate constant K. Okay, rate constant, just because, okay, K is equal to R over R. R times by S squared. K is equal to 8.1 times 10 to the power of minus 5 over 0.76 times by 0.98 squared. .11, I say no, it's two significant figures, so 1.1 times 10 to the power of minus 4. Deduce which of T1 and T2 is higher. Well, I'd say that's T2. T1 was clearly T2. No. Yeah, sorry. T1. Yeah, sorry. Because the rate constant is higher, so rate constant is temperature dependent. So that's just that. Yeah, sorry. Don't worry, it's really late, guys. I'm really sorry for this. The rate of the reaction between substance A and substance B was studied in a series of experiments carried out at the same temperature. In each experiment, the initial rate was measured using different concentrations of A and B. These results were used to deduce the order of the reaction with respect to A and the order of reaction with respect to B. What is meant by the term order of reaction with respect to A? It's the power of the concentration. The power of the concentration of A in the rate equation. So when the concentration of A and B were both doubled, the initial rate increased by a factor of 4. To use the overall order of the equation, so it's just 2. Just half that to 2. In another experiment, the concentration of A was increased by a factor of 3, and the concentration of B was halved. This caused the initial rate to increase by a factor of 9. Okay, so we have 3x plus half y is equal to 9. Now, if I 3 times 2, 3 squared really the power shouldn't be that. It should be more like 3 to the power of x, y to the power of a half. No. A half to the power of y. 3 squared will equal 9. 3 and a half to the power of... I don't think this has any order. I think you can just do order of that as 2. Yeah, because that still would have an order of 2. Because I don't see any other example where you'd have... Yeah, no. Order of respect to B would be 0. I think it's that. I might be wrong, but I'm going to go and look at the mark scheme after this. We still have 3.5 minutes left. Using answers from part C, I write a rate equation for the reaction and suggest the suitable units for the rate constant. So the rate equation, R is equal to K A squared. R would be equal to, sorry, K is equal to R of A squared. So just be moles to the power of minus 1 dm cubed per second. And that is it. Yep. 2 minutes 45 seconds left. So yeah, I'm gonna look at this now. So from experiment 1 to 2, A is doubled and B says constant rate is doubled. Initial rate of reaction is doubled. Yep. And this is 2. I have highlighted or circled it saying that the order of B is 2. So 2 marks for this. So it's very on this mark scheme here, saying that experiment 1 to 2 is doubled, and whilst when A doubled. So I can't speak right now. For experiment 1 to 2, A doubled, but B was constant, so the rate doubled, and the order of the secondary reaction, order of B was 2. So for the next one, showing this here, so you're working out, is a mark. And then 1.1 times 10 to the power minus 4 is a mark. Moles to the power minus 2, dm to the power of 6, s to the power minus 1 units is another mark. If you got 4.4, now, in fairness to this, there are the smallest number of significant figures is 2. So this technically 1 didn't have to be there, but they have allowed it. So that's my mistake. But 4.41 times 10 to the power minus 7. This is why you should go back over your work and make sure that you don't make silly mistakes like that. Like seeing, because I've seen people lose marks. I've seen myself also lose marks because I didn't look at the smallest number of significant figures in the question. So yeah, but this is 4.41 times 10 to the power of minus 7. You don't need to show the units here because they weren't looking for that. So 4 marks in total for this question. Next one, order of P is 2, order of Q is 1, 2 marks. Rate constant K. Rate equation was R is equal to K times by R times by S squared. Then working out the rate. Again, that's my own fault here for not seeing that it's only 2 significant figures. So 4.7 times 10 to the power minus 5. I don't know why I do these videos so late. That would have been fine there. Well, I should have done that in green pen. I just highlight it in green pen because I'm more bothered now. So I would have got 1 mark out of this. I haven't even done the rest of this. This video is such a shambles, but that's a mark. For the second part, just doing this part here is a mark, doing the working out is a mark. Then 1.1 times 10 to the power minus 4 is a mark. Then saying T1, I don't have to explain the reason why, just saying which one it is. And that's a 5 there. So 7 overall from this. It's the power or index shown of the concentration in terms of rate. Yeah, that's same, pretty much more or less the same thing here there. 2, yes, I was right there. This is 2 and a 0. And then the R is equal to Ka squared. Moles to the power minus 1 dm cubed per second. Yes, that's it. So got 6 marks here. I think I got 18. No, 19. Missed out on 1. Either way, 19 out of 20. Hopefully this video was helpful to you. It's probably dragged on way more than it needed to. But that's everything in controls to rates. Rates are now done. So yeah, that's it. Bye.